Thanks for that really nice introduction. It's nice to hear the outreach part of my career highlighted as well. I really appreciate that. As Roberta said, my name's Jessica, and I'm going to be telling you a little bit about the work I did mostly in my PhD, looking at the environmental factors and measurements of the C+ deficit in local universe galaxies. It is 5 a.m. here in California, so if I do make any silly mistakes, let's please blame it on that and just be a little patient, but I think I should be okay. I know this fairly well, and I'm a morning person, so it should be fine. So let's jump right in. So just to start, I wanted to give a brief outline of my planned talk. So I'm going to start with a quick little overview of the problem, as well as just defining what C+ emission is, why it's a useful emission line to measure, and what kind of what we can learn from measurements of the C+ emission, and then transition into what the C+ deficit is and why it's a problem we should be interested in solving. Then I'll briefly touch on the two surveys I used to do my PhD work, the Kingfish and BTP surveys, how we use the data from those two surveys to isolate the C+ and IR emission by ISM-phase, and then how we use those isolated C+ and IR emission measurements to test different causes of the C+ deficit. Finally, I'll quickly highlight some of my current work here at SOFIA, looking at spatially resolved studies of C+ emission in nearby galaxies, specifically focused on the recent work I did with Dario Fata, looking at NGC 7331, and then just wrap up with conclusions. Okay. So like I said, I wanted to start with just why should we be interested in the C+ line? So the C+ 158 micron line, the first reason is just that it's often the brightest observed emission line in normal star-forming galaxies, which can be seen in this kind of typical SED from the Kennicott 2012 paper. There's quite a few reasons for this. C+ carbon is one of the most prevalent elements in the universe. It's number 4, and it has a relatively low ionization potential, which means singly ionized carbon is the predominant phase of carbon in multiple environments across the typical ISM. So there's just quite a bit of singly ionized carbon that can produce this line. It's also a far infrared line, so at 158 microns, it can penetrate dust and gas in a galaxy with minimal attenuation. So unlike most of the hydrogen lines that are in either the optical or the UV, this 158 micron line is in the far infrared, so we don't have to worry about dust attenuation. So because of this brightness, it's detectable in both the local and high redshift universe as characterized by these great detections from redshift of 6 quasars from a DeCarli 2018 paper, where we can just see that with ALMA, we're getting this slew of high redshift C+ detection. So with surveys like Alpine and Rebels, we're seeing just more and more of these redshift of about 4 to 9, I think is the highest I've seen, detections of C+. So there's this hope that we can use C+ emission to study the involving conditions of the ISM in galaxies throughout cosmic time. C+ also plays a really important role as one of the predominant cooling channels for PDRs. So this is just a typical slab model from the recent annual review article by Wafaya Valani-Chavance that came out earlier this year, where they've shown that the C+ line is one of the major cooling lines for PDRs at quite a range of temperatures and AV within the PDR. And this is especially important because it suggests that C+ might be a really good tracer of star formation rate, as the bulk of the heating in a PDR is coming from FUV flux from young O and B stars. So if heating is done by young stars, cooling is done by C+, and we're in a fairly thermally stable ISM, we would expect C+ cooling to directly trace young star heating. And that's essentially what's been seen for the most part. As shown by this plot from the Herrera-Camus 2015 paper, where we can see the surface density of C+ emission matches the surface density, or traces the surface density, the star formation rate surface density, fairly well for the regions within the normal star forming galaxies included in this work. So there's this hope that C+ can be used to potentially as an unattenuated star formation rate tracer across cosmic time. There's also been suggestions that C+ might be a really good tracer of CO dark molecular gas, a tracer of shock heating, or other just properties of the ISM. So understanding this emission and how it relates to galaxy properties can really help us determine how galaxies are growing and changing over time. So with that, I've now told you why C+ is the best line and we should all be studying it. Now I'm going to kind of get into the still kind of unanswered questions about this emission. And one of the biggest ones that I'm interested in is the C+ deficit. So the C+ deficit is shown really nicely here from the Smith 2017 paper, where we can see the luminosity of the C+ line divided, the ratio of the C+ line to the TIR luminosity, the infrared luminosity, decreases by over an order of magnitude as a function of star formation rate surface density. And this is an issue because we know that TIR luminosity traces warm dust. That dust has been warmed mostly by young stars, so we know TIR is a tracer of star formation rate. So if C+ was also tracing star formation rate, we would expect this ratio to be flat because both of them should be increasing as we go to star-bursting galaxies. And we can see that it's not. And so this tells us that at least in these star-bursting galaxies, C+ isn't necessarily tracing star formation rate the way we would expect. Something seems to be happening inside the ISM that's either changing the photoelectric heating efficiency, so there's less heating, so we need more cooling, or it's changing the C+'s ability to cool. So either C+ is becoming a less efficient coolant, or the ISM is becoming a less efficient heat transformation. We're seeing less efficient transformation of UV photons to heat. So understanding why this occurs and how it might affect potential measurements of the C+ line and measurements of ISM properties done using the C+ line is really important to fully utilizing those high redshift detections to understand the ISM. And so that's where my PhD work came in. I was working at University of Wyoming. I was primarily working with Danny Dale and the Kingfish team, where Kingfish stands for Key Insights in Nearby Galaxies, a far infrared survey with Herschel, to look at the C+ and nitrogen-2 detections from star-forming regions within local universe galaxies. So this poster just shows all of the Kingfish galaxies, and the ones with green stars were the ones that had the full suite of panchromatic spectra and photometry that I needed to do my studies. In addition to the Kingfish survey, I also worked with the Beyond the Peak survey, which followed up on 20 of these galaxies using the Spire instrument on Herschel to get wider field of view measurements of the nitrogen-2 line. A big caveat of everything I'm going to present is that all of the galaxies I worked with in this sample are nearby star-forming galaxies. So there's no ULIRGs, maybe there's a few buried AGN, but these are not AGN-dominated galaxies. They're all just, none of them are star-bursting, and they all are within about 30 megaparsecs and have metallicities pretty close to solar. So what I am saying is going to be true of these sources. It might not be true of every galaxy. So that's just a big caveat to introduce. So with the Kingfish survey, 31 star-forming regions in 28 of the galaxies were targeted using the PAC spectrometer at both the 158 and the nitrogen-2 205 micron lines. And so the regions that were targeted are pretty small. This is just an example in NGC 6946, where we had 3 targeted regions, 1 centered on the nucleus and then 2 centered on extranuclear star-forming regions. And you can see that the kind of observational squares that are outlined in green are really just focused on those star-forming regions. So we're not getting much outside of the star-forming regions. So in order to understand what's happening in the more quiescent areas around those star-forming regions, we introduced the Beyond the Peak survey, which had that follow-up with Spire, which has a wider field of view. So was able to target the 205 micron line, not just in the star-forming regions, but also in some of the more quiescent ISM surrounding them. So this gave us a sample of, again, star-forming regions for the most part in local universe galaxies. With these measurements, we could now go through and try to isolate the C+ emission by ISM phase. And this is important because carbon has a relatively low ionization potential at 11.3 electron volts, so notably lower than hydrogen's ionization potential, 13.6 electron volts, which means that we can find the singly ionized carbon that produces the C+ emission in phases of the ISM where hydrogen is ionized, or the ionized ISM, as well as phases of the ISM where hydrogen is neutral, or the neutral ISM. And this just means that changes to any portion of your ISM can potentially affect your C+ line. So it just makes it a lot more complicated to understand what potential effects are causing changes in brightness in the C+ line, because it could just be coming from so many different types of environments. So in order to break down our C+ emission into C+ from the ionized phases and C+ from the neutral phases, we use the singly ionized nitrogen, which has a higher ionization potential at 14.5 electron volts. So we only really expect to find singly ionized nitrogen in the ionized phases of the ISM. So that means all of the N2 emission that we're looking at is coming from those ionized phases, where the C+ might be coming from both the ionized and neutral phases. So just as a really kind of simple model here, if we're looking at a star forming region, we might expect there to be some young O and B stars in the center. This could be surrounded by an H2 region where hydrogen, nitrogen, and carbon will all be ionized. And collisions with electrons are exciting our C+ line. And then at some point, we're going to run out of photons with energies above 13.6 electron volts that can ionize hydrogen, and we'll enter a neutral PDR where carbon could still be ionized, but nitrogen and hydrogen will both be neutral. So by using the strength of the N2 emission, we can kind of predict how much C+ emission we expect to see from the H2 region, and use that to separate out the C+ from the neutral and ionized ISM. And so this plot is just showing essentially how we do this, where I've plotted the theoretical prediction of the C+ to the nitrogen 205 micron line as this solid cyan line, as well as all of our data from the Kingfish and BTP surveys as green and magenta points. And the distance those points fall above the line tells us how much of our C+ emission must be coming from neutral phases of the ISM, where there is no singly ionized nitrogen to produce the nitrogen 2 line. So if these points were falling right on this cyan line, we would say 100% of our C+ emission is coming from the ionized phases. But since for the most part they're not, maybe this one is, we can use the distance above to say how much of our C+ emission is coming from the neutral phases. On this plot, I'll just briefly point out that we use the nitrogen 205 micron line instead of the brighter 122 micron line, because of the relative flatness of this theoretical C+ to nitrogen 205 micron prediction. So this means that even if our measurements of electron number density are slightly off, we can still assume that C+ over nitrogen 205, this ratio should be approximately 4, kind of regardless of what your density conditions are. Now we are able to measure density in our sample because we have both these nitrogen 2 lines, so we use those to get density. But if you were looking at a high redshift source where you didn't have a density measurement, you could maybe still use the nitrogen 205 line to predict this ratio with just setting a value of approximately 4. So this is a good way to kind of test that as well. So once we had these measurements of the C+ from the ionized and the neutral, we could re-examine the deficit with the C+ divided by ISM phase. So this is one of the major results from my 2019 paper, where we just isolated the C+ emission. So on this first panel, I haven't pulled anything out. This is just the total C+ emission before being subdivided by ISM phase, divided by the TIR emission, here as a function of the 70 to 160 micron flux ratio, which is an indicator of dust temperature. So hotter dust would be increasing on the x-axis. And we can see that there's a slight deficit behavior. There's not much of one. This is effectively what we expect for our sample. So we're not looking at any starbursting galaxies. So we see the deficit trend. We don't see a strong deficit trend. That's an effect of the sample. What's more interesting is that when we look at only the C+ emission from the ionized phase, we see a very clear deficit behavior. Whereas when we look at only the C+ from the neutral phase, that deficit behavior is almost completely gone. And we see that nice pretty much flat C plus over TAR emission that we would expect if C plus was tracing star formation rate. And so this got us curious into thinking like, okay, what could be happening that could cause the C plus deficit in only the ionized phases of the ISM? And can we further test this? Because right now, could this possibly just be the fact that we're taking the total TIR emission? So is there a way that we could go back and also divide that denominator by ISM phase? And so this is where things got a little tricky, because we wanted to isolate the infrared emission by ISM phase. And the infrared emission is just essentially emission from warm dust for the most part. So this gets a little tricky, but we worked with some of the theorists in our team and figured we could at least make an estimate of the fraction of this TIR emission from H2 regions using a combination of the Segal SED fitting program along with the DRAIN 2017 dust models. And really specifically, we're working with this equation here from the DRAIN dust models, which gives you the fraction of the dust luminosity that's heated by some interstellar radiation field U greater than a cutoff value. By setting UC, our cutoff value, to the value of the interstellar radiation field we expect at kind of a theoretical Strömgren radius, we can get at least an estimation of the fraction of the dust luminosity that's coming from within an H2 region. So there's probably a lot of kind of hand waving that is happening here and a lot of uncertainty that is introduced with this measurement. But this was our way of at least estimating the fraction of the dust luminosity that's coming from within the ionized H2 region as opposed to the neutral PDR. Just to test this, we plotted our TIR emission from the ionized phase as a function of the 33 gigahertz radio luminosity. And we see for the most part, there's a pretty good correlation between these two measurements, which since we know the 33 gigahertz luminosity should be coming from the star formation, the star forming H2 region kind of area, this is a good indication that we're at least getting a good approximation of the TIR emission from the ionized phases. So with this subdivided TIR, we can go back and relook at our deficit with now both the numerator and the denominator divided by ISM phase. So again, the first panel is the same. I've normalized things now for easier comparisons, but we're still seeing, okay, when we look at the total C plus and the total TIR, there's a slight deficit, not much of one, that's our sample. But when we look at the C plus over TIR from the ionized phases only, we still see that deficit pretty clearly, although now there's more scatter, likely introduced by our method of isolating the TIR emission. And when we look at the C plus over TIR, both from the neutral, we again see that relatively flat kind of relationship, which I showed earlier. So it's not that the TIR emission is messing up our measurements. We're still seeing, if we do try to divide the TIR up, we're still seeing the deficit primarily occurring in the ionized phases. So this got us to the question of what potential cause of the C plus deficit would only happen in the ionized phases of the ISM. And one of the potential things that we came up with was thermalization of the C plus line. And this is because that C plus in collisions with electrons has a relatively low critical density of about 32 per centimeter cubed, which is a density that is often surpassed in typical H2 regions. So it's very likely that C plus can be thermalized in an H2 region. This would lead to TIR continuing to increase since we're still, as we add more young stars, as we increase our star formation rate, so we're still dumping more energy into the ISM, TIR will continue to go up, but C plus would remain relatively constant once it's thermalized. So we would see C plus staying constant, TIR increasing, and that would produce a deficit. Just to note, this would primarily happen in the ionized phases because of the low critical density for C plus in collision with electrons, as shown in this plot from Spinoglio 2014. But the critical density for C plus in collision with hydrogen atoms is much higher, so we don't necessarily expect this to be a problem in PDRs. So this would kind of explain why we're seeing this deficit in the ionized ISM and not in the neutral ISM. So in order to further test this, we plotted our C plus over TIR as a function of density, looking at the electron number density in the ionized phases and the atomic hydrogen number density in the neutral phases. And what was really exciting was that when we looked in the ionized phases, we saw and we plotted a theoretical curve of what we expected our C plus over TIR from an H2 region to be, the data followed the theory really, really nicely. So I haven't scaled anything here. This blue line is just a theoretical prediction made just starting with essentially strong wind conditions and what we would expect to see there. And we can see that, again, it follows our data really, really nicely. Another thing that's exciting is that when we hit the critical density, which is shown by this dashed black line, the C plus over TIR falls off quite precipitously. So this seems to be suggesting that in the ionized phases, we are seeing thermalization. Now in the neutral phases, I've plotted this as well versus atomic hydrogen and then plotted the critical density as a dashed dotted line. And we can see that for the most part, our data points don't reach that critical density. So we don't expect to see a deficit caused by thermalization there. Now the big caveat again, sorry, I'm running out of time, so I'll try to go quickly here. But this can only explain moderate deficit behavior because only 20 to 30% of the C plus emission typically comes from ionized phases. So this works great for our sample, but wouldn't explain an order of magnitude deficit. So there's still a lot of other potential effects. There could be grain charging as suggested by this plot from McKinney 2021, which could lead to changes in the photoelectric heating efficiency and a decrease in the C plus over TIR. There could be effects from AGNs that could produce more infrared radiation unassociated with star formation, and so not as much C plus. Other far infrared lines could become dominant cooling channels, although I will note this seems to have been disproven by seeing deficits in these other far infrared lines as well. And then in Milky Way studies, they've also seen the effects of C plus self-absorption. So that could also be occurring in these high redshifts, in these more starbursting galaxies, and could be causing problems as well. Although this is also complicated by the fact that we can't really do these measurements in other galaxies very well. So just as a really quick highlight of what I've been doing here at SOFIA, Kingfish and BTP mostly focused on nuclear regions. So I've been working with Dr. Dario Fada here at SOFIA to try to expand the areas within a galaxy that we can look at in C+ by mapping the C+ in kind of the more diffuse disk. Specifically, we recently published on NGC 7331. So this is just the infrared map as well as the C+ map, where we can see that we detected C+ both in the nucleus, the infrared bright molecular ring, as well as some of the spiral arms and the diffuse interarm media. And we were able to then measure the C+ deficit as a function of environment and see that in the nucleus, we saw the lowest C+ over FIR, whereas in the spiral arms, we saw the highest. And we were also able to get this nice connection between our local measurements, the Kingfish star forming region, and the gold sample of ULIRGs. So I'm hoping to continue this to using archival C+ maps and isolating by environment, looking at both PAX and FIFI-LS, looking at both the PAX and FIFI-LS archive, and then compare C+ with PAH and also CO emission to see if we can see a correlation between C+ and potential areas where there might be CO dark molecular gas. And since I think I'm over time, I just will leave my conclusions up and just thank all of the funding agencies and teams I've been able to work with, specifically the NASA Earth and Space Science Fellowship, the University Space Research Association, the SOFIA Science Center for allowing me to continue this work, and then the Kingfish team, especially my advisor, Dr. Danny Dale, for working with me to produce this.
Thank you, Jessica, for the very interesting talk. I will stop here the